So you had this, this is what is happening here. So you had this one word embedding, okay, hi, let's just call it h1, right, if you want, h1. You did this linear transformation, right? So let's say this was an RT dimensional embedding, then you could multiply it by a D cross D dimensional matrix and again get a D dimensional vector, right? You could do the same thing at all these three places, right? So from now one vector, you have been able to generate three vectors, and you needed these three vectors because three vectors were participating in your attention equation earlier, right? So you have these three vectors now. Now, what do you do with these three vectors? So these are, let's just look at their names again. So this was all the HIs that you had, or the HJs. These were your matrices. These were the learnable matrices, the transformation matrices, WQ, Q for query, WV, V for value, and WK, K for key. And what you get out is the query vector, Q, the value vector, V, and the key vector, K, right? So for each word, from your perspective, for each word, you have now been able to create three vectors from it, right? Now, how do you use these vectors? How do you compute the attention is something that will come later on, right? But for now, what we're doing is something simple, right? For whatever reasons, we're taking one vector and computing three vectors from it, and these three vectors are being computing with the help of linear transformations coming from a matrix, right? So, and these are learnable parameters. So, you have already introduced some parameters into the mix, okay? Yeah. So, I'm just repeating what I had said on the slide, and these are called the respective transformations. Now, so now let's focus on computing the output for the first guy, right? So this is the first input, right? Let's see. So you have h1, h2 all the way up to h5, and now let's see how z1 gets computed, right? Which is the contextual representation for the word I, right? And through the self-attention layer. And what do these query, value vectors that I showed, how do they play a role in this, right? So let's see what is going to happen there. Yeah. So I'll just zoom into this. I'll just clear the annotations. So you had this single embedding, which was h1, right? And from there you can see there are three arrows coming out. So you would have realized that I'm going to compute three different values from this one vector, right? So let's see what those three values are. Sorry. So I'll first do a linear transformation with WQ to get a new vector, which is I'm going to call as the Q vector. So this is going to be the Q1. Similarly, I'll do a linear transformation with K, and I'll call it as K1. Similarly, I'll do a linear transformation with V, and I'm going to call it as V1, right? Now, how I'm going to use this Q1, K1, V1 doesn't matter, right? But at least pictorially, you get to know what is happening here. I had one vector. I did three linear transformations to get three different vectors from that. I'm calling them as Q1, K1, V1. I'll continue the same for all the all my words in the input. All of this can be done in parallel, of course. So I'll again take the last word, for example. I'll do this for all the word, but I'm just showing it for the last word again. So I'll take H5 in this case, pass it through WQ, and I'll get my Q5. Similarly, I'll get K5, and similarly I'll get V5, right? So if I had T words in the input, I have computed this 3 into T vectors using these linear transformations, okay? Now what next? What am I going to do next, right? So now what I want to do is, I want to compute, earlier I was computing the score. Let me just flash the equation and then I can do it, right? So earlier I was computing the score between st minus 1 and hj, and this was used to give me the importance of the jth word at the tth time step, right? So again, now I'll have some score, and my indices would be I and j, right? The ith word and the jth word. But now what does go here? That's the question, right? So let's see what goes here. So the function that I'm going to use is to compute the score between q1 and kj, right? So now this is my query vector. So I'm interested in knowing the weights of all the other words with respect to the first word. That's why that's my query. The query is the first word, and I want to understand the importance of all the words with respect to that word. So I'll pass different values of k, k1, k2, k3, k4, k5 through it and compute the score, right? So I'm going to compute 5 such scores, right? So earlier this was the st minus 1 was fixed, right? because that was the state of the decoder at time step t minus 1. That did not change. So that was in some sense my query, because for at time step t I was interested in knowing the weights of all the input words. Now with respect to my query, or my first word or my word of focus, I want to know the weights of all the other words. So that word is going to remain fixed. I'm going to have q1 and I'm going to compute capital T such values, right? So each telling me the importance of the first word, second word, third word, fourth word, fifth word, right? Notice that I'm also computing the importance of the word itself, right? That also I'm doing. So q1 with respect to k1, k2, k3, k4, k5, right? So q1 with respect to k1, k2, k3, k4, k5. So these 5 scores I'm going to compute, and maybe I'll call them as A's. Okay. Now the function that I'm going to use is just the dot product. Like, what is the scoring function? My scoring function is just dot product. So my E's, which are the unnormalized attention weights, are just going to be the dot product between q1 and k1, q2 and q1 and k2, q1 and k3, all the way up to q1 and k5. Right. So as I had mentioned here, q1 remains fixed, and I just keep changing the key. That means the word or the representation with which I want to compute the attention, right? So that keeps changing. So I'll get some dot products here, which would be some real values, and the way I'll compute the alphas from that is that I'll just do a softmax on this vector, right? So that's what this equation is saying. To compute alpha, so this is E11, this is E12, all the way up to E15. So to compute alpha 1, 2, I'll just take I should have chosen my variables carefully. So e raised to e 1, 2 divided by the summation over all e's, right? That's what I'll do, right? So I'm just going to take the softmax here. Now once I've taken the softmax, that gives me the alphas. But how am I going to compute my z? My z is going to be a weighted sum of the inputs, right? And what are the vectors that I'm considering as input? I'm considering the v's now, right? So these are known as the value vectors, right? So q and k participated in computing alphas. Once I'm going to compute alphas, my new representation, which is z, is going to be a weighted sum of the v's, right? So you have all the 3 vectors participating in this computation. Q and k participated in computing the alpha, and then there was a v, right? Just as you had a v sitting outside, if you remember, right? You had this v getting multiplied by everything that was happening inside, right? So you had this va transpose tan h into something something, and this is where st minus 1 and hj were. So they were participating in computing this, and finally you get a vector and then you multiply it by this, right? So similarly now the vj's here are participating in the final computation that you have, right? So z1 is going to be computed this way. Now how do you compute z2? The same story, everything remains the same, right? So now you would have q2 as the query, right? So your e2s would be the dot product between all the q2 and all the vectors. Then you will compute the alphas as the softmax. Once you have computed the alphas, these are all alpha 2s, you will compute the z as a weighted sum of your 5 input vectors, and the weights would come from the alphas, right? So very easy to understand now. You had one vector, you had h1 to h5. From each of these h1, h2, h5, you computed 3 vectors using the query transformation, key transformation, and value transformation. The query vector is used to find the importance of all the words with respect to this word, right? So this is fixed, and you're trying to find the importance of all the words. So the vector contains the dot product between your query and all the keys that you have. Once you have computed the importance, now you need to take a weighted sum of all the words. So for taking the weighted sum, you look at the value vector, right? So that's how you have these 3 vectors which get used in this computation, right? So I think it's should be pretty clear from the diagram and the equation how these zi's will be computed. So you'll just do this z1, z2 for all the z's, right? Now let's see if we can vectorize all of these computations, right? That means, can we compute the z1 to zt in one go, right? So here I first told you how to compute z1, then I told you how to compute z2, and then similarly z3 up to zt, right? But my whole point was that I don't want to compute these outputs sequentially, right? That's why I didn't like RNNs, because the output of the RNN, if this was the RNN block, then these outputs were coming one by one. And at the end of all this, I don't want to do the same thing again, right? I want all of these to come out in parallel, otherwise it doesn't help me, right? I might as well have stayed with RNNs, right? So now can I do this in parallel? So now let's see how I'm computing Q1. Q1 was the matrix WQ multiplied by H1. How would I compute Q2? It would be the matrix WQ multiplied by H2, right? And that would give me Q2. How would I compute Q3? It would be the matrix WQ multiplied by H3, which would give me Q3 all the way up to H capital T. So it would be WQ multiplied by HT, which would then give me Q capital T, right? So now I can just write this as a matrix operation. You can just put all of these vectors inside a matrix, and if you multiply this matrix by this matrix, then you get this matrix as an output, right? So all the Qs you can compute at one go, right? You don't need to do that sequentially. All the query vectors can be computed at one go by just multiplying these two matrices. WQ multiplied by the matrix containing all these inputs as columns, and then you get the Qs at one go. Similarly, now what is the dimension of Q, right? So let's look at that, right? So let me see how to do that. So this is say the input dimension was D, right? And for I'll just take D as 64 for the purpose of explanation. So this is a 64 cross T matrix, right? So each of these is 64 dimensional, and you have T such entries. Now this would get multiplied by say so this would say get multiplied by a 64 cross 64 matrix, right? So you could have just thought of this as D cross D and this as D cross T. So these two matrices multiply and I get a D cross T output. In my case, I have just taken D as 64, right? So this Q would also be of the same size as your input representation, but you could have different sizes also, right? So if you had chosen this as D1, then your output would be D1 cross T, right? And so you could have either the D1 could either be bigger than D or smaller than D based on whether you want to just project to a smaller space or a higher space, but that is not the main point here, right? The main point is that you had T inputs and you have T outputs, right? This is not changing, right? This capital T remains the same. That means you had T input representations and now you have got T query representations from those T input representations, right? What you choose the size of D1 and D2 is up to you. In this example, I have chosen it as 64, both D1 and D equal to 64. So if my input, this was 64 cross T, my output would also be 64 cross T, right? What is important as this T, that you had T inputs and you got T outputs in parallel, right? You got, you did the entire computation in parallel. Similarly, your value, your key vectors you can compute in parallel. So you have Wk multiplied by H1 gives you K1, Wk multiplied by H2 gives you K2, and so on. So you might as well stack them up in a matrix and then you do these two multiplications, so you'll get K1 to Kt in parallel. Again, the key thing here is you had T inputs, right, and you got T outputs in parallel, right? So your K matrix is also going to be something cross capital T. Right, that's what is important, that you get T outputs. And lastly, same for the value matrix also, you'll get these T values in parallel, right? So now you have already parallelized the computation of the K, Q and a V, right? So that at least I don't need to do sequentially. Now can I do the rest of it also in parallel is the question, right? So let's see how I can compute the entire output in parallel, right? So this is how I can compute the entire output in parallel. So what was I doing earlier, right? So how did I compute Z1? So now can I compute the entire output in parallel? That means can I compute all the Zs in parallel? And yes, you can. So this is what your Z matrix would look like. Again, it would have these capital T outputs and all of them can be computed in parallel by using this equation. How does that make sense? So what did I want, right? If you remember, I had started with this wish list that I had these words, I am enjoying blah blah, and then I am enjoying blah blah. So this was a T cross T matrix, right? So I had to compute this T cross T attention matrix. Is that what is happening here? Indeed, right? So if you remember, Q was 64 cross T, so Q transpose would be T cross 64, and K was T cross 64. Oh, sorry, 64 cross T. So when you are multiplying these two matrices, you are getting a T cross T matrix, which is essentially the attention matrix. And now once you have the attention weights, you are multiplying them by the value matrix, right, which contains the V1, V2 up to Vt, right? And now if you take the product of these two matrices, then you will again get a T dimensional output, because this is D cross T, and this is so this is V transpose, sorry. So this is going to be T cross D, and this is T cross T matrix. So this two will multiply to give you a T cross D output. So you'll get capital T Zs, each of which is going to be D dimensional, right? So you can do the entire computation in parallel, and you can make sure, right? You can go and check this back, that if I were to look at, let's see, right? Like we can just do it right away. Yeah, so what I would like to show is that Z2 is indeed, if you do this large matrix multiplication, Z2 indeed comes out to be the same as what we had seen in the figure, right? So let's try to do that. So I'll just start from scratch. So I had this T cross T matrix, which was Q transpose K, right? So if I look at the second row of this matrix, right? So let's see what is happening here, right? So this was Q transpose. So this was Q1 transpose, this was Q2 transpose, and so on. And this was K1, K2, and so on, right? So if I look at the second row of, so any ijth value of this entry of this matrix is just going to be Qi transpose Kj, right? And in particular, if I were to look at the second row of this matrix, it is going to be Q2 transpose K1, Q2 transpose K2, and so on up to Q2 transpose Kt, right? That's what the second row is going to look like. And now that this matrix Q transpose K, this is what the Q transpose K matrix looks like, is going to get multiplied by V transpose, right? So then this would have V1 here, V2 here, and so on, right? And if I multiply these two, what is the second row going to be? The second row is going to be a linear combination of all the rows of this matrix where the weights are these, right? And that's exactly what I wanted. I wanted Z2 to be Q1, Q2 transpose K1, right, which was alpha 2 1 multiplied by V1, and then alpha 2 2 multiplied by V2, and so on. And that's exactly the computation which is happening here, right? So that's why this entire thing can be produced as matrix multiplication, and all of this can be done in parallel. So just to recap, your V's can be computed in parallel, your K's can be computed in parallel, your Q's can be computed in parallel. Once you have that, you get all the Z's in parallel at one shot, right? So that's what is happening here. So you're able to compute, you're able to parallelize the entire computation of your Z. And what actually is Z, just in case you have forgotten? So you had the input as H1, H2 all the way up to HT, and Z was the output of this network, right? And my main goal was that this output should be computed in parallel as compared to RNNs, where I was getting 1, then 2, then 3, and then 4, right? But now I've shown you that all of this can be done in parallel, and you just need to execute this matrix multiplication, which is in turn has many matrix multiplication. V itself comes from a matrix multiplication, K comes from a matrix multiplication, Q comes from a matrix multiplication. Once you have that, you do these matrix multiplications and you get the Z at one go, right? But all of this is parallelizable. I don't need to wait to compute ZT minus 1 to compute ZT, right? That's the main takeaway that I have here, right? And you see something here which is you're scaling it by the dimension, right? So this D was 64 in the examples that I had done. So there is some justification for why you need to do that. I'll not go into it, but for all practical purposes, you're taking the dot product and then just scaling it by some value, right? So this is what the dimensions look like, as I had already explained. So you get all the capital T outputs, and since you're taking the dot product and then scaling it, this is known as scaled dot product attention, and this is how you should look at the series of operations happening here, right? So you had Q, you had K and V. You did a matrix multiplication to get Q transpose K, then you did a scaling to get the scaled output, then you did a softmax on that, and then whatever you got as softmax, which would have been a matrix, right? This softmax of this entire thing, this is again going to be a T cross T matrix, which is going to get multiplied by a T cross 64 matrix, and that's the matmul that I'm talking about here. And then finally you will get a T cross 64 output, right? So this is the attention that you get, this is the self-attention layer block that you have. This is what the full block looks like. It starts with these linear transformations, then the matrix multiplication, softmax, and then again matrix multiplication to give you the capital Z at the output, which in turn contains Z1, Z2 all the way up to Zt, right? So we have been able to see the self-attention layer, which does a parallel computation to give you a contextual representation for the input vectors that you had provided, right? So I'll stop here, and then in the next lecture we'll look at multi-headed attention, and then I'll talk about a few other components of the transformer network. Thank you.